at the mechanics of rigid bodies. So I have mine right here, this roll of tape that we're gonna assume to be an ideal ring. And for my problem, I'm gonna see if I push with a certain force at the very top of this ring, if we can find the acceleration about the center of mass and the angular acceleration of this roll of tape. So.
All right, so let's go over the kinetics of this roll of tape. So here is our initial sketch of our problem. So we have the radius of the roll of tape, and then we know we have an applied force, and then we know we're trying to find the angular acceleration and the acceleration about the center of gravity of our object. So some givens and assumptions, we were given that our applied force is 0.5 newtons, our mass is 0.3 kilograms, our radius is 4.5 centimeters, and our mu static is 0.25. And then we're assuming there's no drag, that we're not slipping, so we only have static friction and not kinetic. And then we're assuming that we have an ideal ring where all the mass is compiled at the outside of the ring. And then our gravity is negative 9.81 meters per second squared. So here's our free body diagram and our inertia diagram. So if we look at the left here, we establish our coordinates with y being positive and going up, x being positive to the right, and then a change in popular convention. We have our positive moments going clockwise instead of counterclockwise. So in our free body diagram, we have our applied force, of course, and then we're going to have the force of friction acting at the bottom of the roll of tape, and then we have our normal force and our weight. And then looking at the inertia diagram, we know that we have acceleration in the x direction, and then we have our angular acceleration, and then we marked our points G and A. A is the point of contact of the ground, and G is our center of gravity. So here is our analysis. So we have the sum of forces in the y equals mass times acceleration in the y direction. We know that acceleration in the y direction is 0 for this problem. So we just have our normal force minus our weight. So our normal force equals our mass times gravity. So 0.3 kilograms times 9.81 meters per second squared. And then some information that we will need for our moment equation later. Our moment of inertia is m times r squared, because we are dealing with a ring, so all of our mass is on the outside instead of like a uniform disk, which would be 1/2. So I equals 0.3 times 0.045 meters squared. And then we also know our relationship between acceleration and angular acceleration. So our acceleration about the center of gravity is equal to our angular acceleration times our radius, which is 0.045. So looking at our moment about A, which was this point at the point of contact of the roll of tape and their table. So we have our force, our applied force times the radius plus the force of friction times the radius is equal to I times alpha plus our mass times acceleration of gravity times r, which is 0.5 newtons times 0.045 meters plus 0.25, which is our coefficient of static friction times our normal force multiplied by the radius of 4.5 centimeters or 0.045 meters is equal to I times alpha plus 0.3, which is our mass, times acceleration about the center of gravity multiplied by the radius once again. So just looking at this, we see that both our applied force and our force due to friction will cause clockwise motion for this roll of tape, which we establish as being our positive. So we all know that all of those will contribute to a clockwise moment. And then plugging in our value for I and our value for AG, we can solve for our angular acceleration, which is 90.5 radians per second squared, and then multiplying that by our radius, we can get our acceleration.